Now, all right. So today we are going to be talking about acids and bases and pH. We're going to get into this today and we're going to kind of extend it a little bit more on Thursday. The slide deck that I'm using is a little bit different from the one that I made some edits to it, the one that we typically, or the one that's posted on Canvas. Um, the nuts and bolts are still there. I just made some modifications to it. But as is always the case, I will be posting my marked up version of this slide deck for you guys a little bit later today. Um, in the meantime, though, what I'm curious about is I've got a couple of poll questions. Whenever you hear acids and bases, what comes to mind? Got a couple of poll questions. This is a group of four questions, so go ahead and answer all of them. First is, are you ready to learn? You got an option. I'm ready and ready to go. Not quite. Coffee's still getting there. Then next question is when you hear acid or base, what comes to mind first? We got a couple different options. The third question, and these should all appear as one thing. The third option is which of the following best defines an acid? And then the last one is at the molecular level, what best describes how a base behaves? So I'd like to see you guys go ahead and answer those. I'll give you a little bit of time on all these questions. And we got quite a few poll questions to go through. So there's going to be no shortage if you miss any of these. Now, I'm really just looking for, well, have you ever heard the term before? And have you ever thought about it in terms of chemistry? So that's, I'm sure that you've seen them in movies or you've heard about acids. And if anyone's ever watched Breaking Bad, they talk about acids quite a bit in that show. Actually, from my experience, that when they talked about or when they used an acid, um, that was whenever I stopped watching the show. It was a bit too violent for me. I'm I'm boring. I will confess. Now, with that, I would like to see you guys. We're going to try something new. I'm going to go ahead and end the poll question. And again, if you haven't answered it, there's plenty more. So there's plenty more opportunities to participate. I'm going to end it now. What I want you guys to do here is if you go to annotate, or actually in the lower left-hand corner of your screen, you'll see a little pencil icon. And if you click that, then that means that you have the power to mark all over the screen. What I want you guys to do is activate that and then mark on any one of these chemicals, just to draw a little X to indicate which of these chemicals has an acid or which of these substances has acid in it. I'll just kind of demonstrate a little X done. I can see you guys' markings on there. And I'll give you a little bit of a hint. There are more than one or more than one substance on here has an acid. Well done. Well done. Okay. Now I'm going to go ahead and disable the annotation for others. I'm just looking kind of for a general kind of quick survey. I'm going to disable annotation. And it seems like the most popular substances that you guys think have acids are Dr. Pepper, possibly because you know that from drinking Dr. Pepper, possibly from, maybe some sensation you've had, oh, I drank a Dr. Pepper and it burns my throat. And that's what I think of when I think of acids. We've got Drano that's popular, pretty consistently popular, the pool sanitizer, and vinegar. Well, I will tell you guys there are two that you selected that are correct, and two of them are actually bases. Now I'm going to clear all the drawings. Uh, and I'll show you. We've got acids, bases, acids, bases. Okay, so Dr. Pepper, has acids in it. Specifically, it's got phosphoric acid and carbonic acid. Um, Sorry, I lost my cursor for a second there. Windex is a base. Drano is a base. The pool sanitizer is a base. Vitamin C is an acid. And last but not least, vinegar is an acid. Now, did I expect you guys to know these? Not necessarily. If you look on the side of well, I've got a Diet Dr. Pepper can here. One of the things that pops up pretty early on is, and I don't know if you can read that, phosphoric acid. It is let's see, first is carbonated water, caramel color, aspartame, phosphoric acid. So that's the fourth ingredient on that list. Now, a fair question there, whenever you think about acids, is, well, what where does that originate from? What's the significance of something being an acid or not being an acid, something being an acid or something being a base? Well, this is something that I always like to bring up with my wife, and that is that I was a history minor as an undergraduate. I was a biochemistry major, but a history minor. And I bring that up to you guys because I'd like to give you a little bit of a history lesson. In 1884, and I don't want to get too political here, so please, reserve your opinions on his presidency to yourself. But in 1884, Grover Cleveland was elected president. In addition to that, in 1884, Ed Haley of the Haley Brothers published the hit song The Fountain in the Park. I think we all know that one. While strolling in the park one day, all in the merry month of May, a roguish pair of eyes, they took me to by surprise. In a moment my poor heart they stole away. Oh, a sunny smile was all she gave to me. Instrumental phrase. I'm going to stop right there because, you know, I don't want anyone who is a fine arts major to feel intimidated by my singing ability, and my ability to maintain a certain tone. So I'll just stop there. But these were two significant events that happened in 1884. Fantastic. But guess what else? And guess what's maybe a little bit more relevant and important to acids and bases? In 1884, a fellow by the name of Svante Arrhenius finished his PhD, and his doctoral dissertation was about acids and bases. And he came up with this theory, basically. And people knew about acids and bases up until then, but there wasn't really a theory as to what an acid and base was. His theory was that in an aqueous solution, in water, an acid would produce a hydrogen ion or H3O plus, which is also known as a hydronium ion. I'll go into those definitions a little bit later on. But for the time being, we're going to kind of treat these as interchangeable, and I'll describe why a little bit later. So a acid would produce these things. A base would produce hydroxide. And the scientific community at the time said, well, that's good. That works for us as a nice definition. But what about something like this? NH3 plus HCl yields NH4Cl. No water is present. So how are we having something act as an acid or a base? And Arrhenius didn't really have an explanation for that, but nobody else did either at the time. This is in 1884. Now, to bring this back to what we were talking about a little bit ago, I want to show you all of these different substances. I mentioned that Dr. Pepper had phosphoric acid and carbonic acid. Well, carbonic acid right here, H2CO3, will produce a hydrogen ion. NH3, well, is that an acid or a base? It doesn't really, it's not something that's captured by Arrhenius's definition for an acid or a base. Well, Drano, by comparison, has sodium hydroxide, and that will release a hydroxide ion. Okay, so that is captured by a base, or Arrhenius's definition of an acid or a base. Sorry, our vitamin C or our ascorbic acid, well, that will produce a proton in a solution. The vinegar will also produce a proton in solution. So from Arrhenius's definition, something like carbonic acid here, found in Dr. Pepper, would be captured by that definition. That definition is adequate to describe this substance. Now, Arrhenius's definition, if it were applied to the active reagent in Drano, that being sodium hydroxide, that would also be explained. So, carbonic acid meets the Arrhenius definition. Drano and sodium hydroxide meets the Arrhenius definition. Ascorbic acid meets the Arrhenius definition. And vinegar meets the Arrhenius definition. Okay, could everyone give me let's go with a Z in the chat if you these, um, follow why these are explained by the Arrhenius definition. Okay. Okay, so I got a private message that said, did he come to this conclusion because he observed it, like actually saw the hydrogen ion, or did he use a different method? So he didn't, it's not a matter of like he saw the hydrogen ions. It wasn't something that's visible to the naked eye. Um, and I don't know enough about kind of what his methodology was, and that's a fantastic question. And you know what I think I'll do is I'll look into that and bring it back next time. I'm guessing at the time that there was some sort of indicator that made it so you could detect an acid. But that was a fantastic question. I will bring that back up on Thursday. So how? Yes. So Oh yeah. That's the person who sent the private message followed up with no clue when we had the technology to see ions, so that was a shot in the dark for me to ask. That is a fantastic question, and that's like an obvious question. I mean obvious, like it's a great question. That's right there. So great question. And I will bring that back up on Thursday. Now, what this gives us basically is of these six household chemicals. With the Arrhenius definition, we could classify four of them. We could not classify all six of them, or the Arrhenius definition would not adequately explain these other two substances. But I already told you that Windex, for example, and the pool sanitizer, they are both classified as bases. Now, with that in mind, it's important to think, well, we had to kind of progress onwards from this. Now, we didn't have a definition for, well, NaOCl or NH3 because these didn't necessarily give us the hydrogen ion or the hydroxide ion that we were looking for. Now, in 1923, Johannes Bronsted and Thomas Lowry theorized, and this is independently. This is pretty cool to me, and I think that it's pretty fascinating. These two people were working on basically the same thing. They were both working on acids and bases, and they both arrived separately at a conclusion and kind of a definition. And they came up with, well, an acid is a proton donor and a base is a proton acceptor. Now, Johannes Bronsted here on the left and Thomas Lowry on the right. If I remember correctly, Bronsted was in Sweden and Lowry was in England. So it's not like, oh, they were working down the hall from one another and lo and behold, oh, we have the same great idea. They're separated by geography. Now, at the time in 1923, the scientific community says, well, and this might not be a direct quote, and just so you guys know, these are kind of suppositions, not direct quotes from the scientific community. Well, that works for us. At the same time, someone named Gilbert Lewis has an even more robust definition, but we think that the students of Dr. Gray's Chem 1310 class should focus on these in the fall of 2025 for their exam on November 20th. Again, not maybe a direct quote, but at any rate. So we have this definition that is kind of revised. It's like an improved definition. And let's see how this applies to, well, our two substances that were not captured by the Arrhenius definition. I'm going to put the check mark back by Dr. Pepper, Drano, vitamin C, and vinegar. Those are all captured by the Arrhenius definition. So those could be classified as acids and bases respectively. Now, the question then becomes, well, what about Windex? Well, the Bronsted-Lowry definition says that, well, it's a base. The pool sanitizer, also a base. And so the question is how? Well, what they theorized was that NH3 will react with water and pick up a proton. Okay, so what that means is that, and actually go ahead and add an A or D. An A for accepts and D for donates. Does NH3A accept or D donate a proton? And when you're accepting, it's like, well, starting from the left-hand side over here, what is different from the left to the right? Has the NH3 gained a proton or has it given up a proton? And it looks like everyone's pretty accurate with their responses that A, it is accepting a proton. So if something accepts a proton, we can go back, a base accepts a proton. So that's how we arrive at this definition of, well, Windex or NH3 is a base. Now, the pool sanitizer. Okay, so that compound is NaOCl. That's sodium hypochlorite. Now, in a solution, this will dissociate into two different ions. One of those is our sodium ion, Na+. The other is this right here, OCl-. That's the hypochlorite ion. Well, that hypochlorite ion will react with H2O. And when it does, it will form HOCl. Okay, so what that means is that OCl it's accepted a proton to become HOCl. And in the process, we're also, and this is the same for the ammonia, we're producing OH. We're producing OH. So by OCl and NH3 both accepting a proton, they are both classified as bases. Now, can you give me a 7 in the chat if, okay, I follow that. And now I can see that all 6 of our compounds that are present here are classified as acids or bases based on the Bronsted-Lowry or the Arrhenius equation, or the Arrhenius example. Okay, fantastic. So essentially what that gives us is we have two theories of bases. We have the Arrhenius theory, which is a little bit older. And these terms theories, I remember the first time I saw this, I was like, well, that's a little bit confusing. Why isn't it a definition? Well, think about this. As Arrhenius had a theory, and he said, this is my theory for what explains everything as an acid or a base. And there were some deficiencies in that. So then Bronsted-Lowry, roughly 40 years later, they say, hey, things that were not captured by the Arrhenius definition, here's our theory to explain other things that are not captured by or not explained with that. So I think that it's a good thing to think about, well, is it a theory or is it a definition? Well, it's a theory because theories evolve, they change over time. A definition is pretty concrete, and basically it's kind of not really going to be wavering. Okay, now the Arrhenius theory, just as a little bit of a summary, it only works in an aqueous solution. It doesn't explain something like ammonia as a base, so NH3. Now, the definition says that, well, an acid will produce protons in water, and a base will produce hydroxide ions in water. Now, that was later revised, or developed, I guess you could say, for the Bronsted-Lowry definition in 1923, or Bronsted-Lowry theory. This is addressing some of the shortcomings of the Arrhenius theory. It works in any solvent, and it puts it in a proton-centric way, or describes it central to protons. Simply put, an acid is a proton donor and a base is a proton acceptor. Now, as a little bit of a way that I like to think about this, and what I think is a simple learning tool, is Well, how do I keep these definitions or keep these theories separate from one another? Well, Arrhenius, I think about that taking place in water. And so what I like to say is Arrhenius likes to go swimming. This is an acid-base definition that only works in water. Now, Bronsted-Lowry, well, there's two of them. So when you have two parties or two people, they can transfer things. So that was helpful for me whenever I took this class to think about it as Bronsted-Lowry, they are transferring protons. One person has a proton, gives it to the other. And of course, we're talking about not people transferring protons, but different substances. Okay. Could everyone give me a 9 in the chat if you're feeling all right about the differences between Arrhenius and Bronsted-Lowry and acids and bases in general? Wonderful. Okay. Now, with that said, what we've looked at are some different substances that you maybe are familiar with, but me haven't, and we've looked at it kind of postulated or looked at a couple of theories with respect to acids and bases, but let's talk about how this relates to maybe some things that you've experienced. Now, give me a 1 in the chat if you have ever had any of these. Atomic warheads. I remember when I was in third grade, that was like the proving ground. Oh, if you could have I feel like there was one that was like the most sour. I feel like these are good examples to explain an acid because, well, they have lots of acids in them, and that's what gives you that tart, sour taste. By comparison, a base, and I'm talking about these in general, like how would you, like if you had an acidic solution or if you had an acidic substance, when you consume something, why does it taste sour? Well, it's probably because there are some acids in there. Now, a base by comparison, if you look around and try to find some substances that are basic that really capture this definition in that they taste bitter, or they feel slippery, it's not super common. Um, but baking soda is a good example. If you've ever added baking soda to water, and maybe you've gotten like a glass of water and added baking soda to it, one of the things that you notice, and this doesn't have to do with it being an acid or a base, but what you'd notice is that that powder, that baking soda, doesn't really go into solution very well. It doesn't mix very well. But as soon as you've added in there, get the spoon stirred around, and you put your fingers in there, it's got like a slippery type of feel to it. In addition to that, if you were to taste it, it's going to taste a little bit bitter. Okay, so these are two properties, or properties of an acid and properties of a base. Now, in addition to that, here what we have is an animated GIF of sodium metal, which is highly reactive, sodium metal in HCl. Now, when sodium metal reacts with HCl, it's going to release H2 gas, and that metal, that sodium, is going to dissociate or dissolve into ions like Na+. Now, this is true of all of these substances. Potassium, sodium, lithium, barium, strontium, calcium, and so on. These are all what are known as active metals. Now, one of the things that I think is a good way to kind of keep some of these active metals straight and to look at a particular place in on the periodic table is to look at, well, columns 1 and 2. So at the top, we have basically our most reactive metal, and that is K, potassium. Below that is sodium. Then we've got lithium, barium, strontium, calcium, magnesium. These are all reactive metals. If you add these to HCl, they're all going to turn into their ion forms. For instance, Li plus or Mg2 plus. And this gas that's going to produce or be produced is H2 gas. H2 gas is going to be pretty flammable. So I'd like to add that to our list of properties of acids and bases. So property of an acid is it will dissolve an active metal. A base isn't going to do the same sort of thing. Now, one thing that is also important when it comes to detecting acids and bases and I guess, yeah, I would say identifying them is, could anyone give me a cue in the chat if you've ever heard of litmus paper? If you've never heard of litmus paper, that's fine. Now, litmus paper, one, you can buy it on Amazon. And if you go to Amazon and you look for litmus paper, you're going to find a couple of different types. You're going to find blue litmus paper, red litmus paper, and neutral litmus paper. You might also find something like this. This is These are pH test strips that are a little bit different because they're a little bit more precise and quantitative, but they are not, and they are going to have kind of a different response. Now, when it comes to these different types of litmus paper, these are very good for detecting if something is an acid or a base or it's neutral. So, is it acidic? Is a solution acidic? Is a solution basic? Is it neither of them? Neither acidic nor basic. Well, in order to do a litmus test, you have to have this type of litmus paper, and these all tell you different things. Now, if we look over here on the left-hand side, we've got a piece of paper that has been dipped into this solution. This paper started out as blue, and then when it was dipped into this solution, it turned to kind of I'll say a pinkish red or a reddish pink. I'll go with pinkish. Now, on the right-hand side, the opposite is true. This paper started out as red, turned blue. Okay, now, when you look at these two different strips of paper, well, a blue strip of paper is one that if it turns pink or turns red, I'm going to change this just so I can be uniform because this is what I got on other slides. If it turns red, then that means the solution is acidic. Okay, so this solution right here that I'm going to put a big star on, would you describe it as A acidic or B basic? Respond in the chat, please. Absolutely, we see that color change. Now, on the right-hand side, we've got a red strip that turned blue. Well, what do you think that this solution is right here? Where I'm going to put, rather than a star, I'm going to put a square. Do you think that this solution is A acidic or B basic? Yeah, this solution is basic. So you could kind of think about this as blue paper can tell you, is it acidic or not? If you took this blue strip and you dipped it into a basic solution, would you expect it to C change color or N not change or NC not change? Blue strip into basic. Yeah, it's not going to change. Okay. A red strip tells you, is the solution basic or not? So if you took a red strip and dipped it into an acidic solution, it's not going to change. Now, this neutral litmus paper is going to be pretty dynamic. If it goes to like that pinkish or brighter red, well, then that's a good indication that you have an acidic solution. If it goes blue, then you have a basic solution. Now, like I said, if you have strips like this where there's multiple different colors, then you're going to see, and actually, if you look at this right here, it's got an entire range of different pHs, which we haven't talked about pH, so don't stress about that. I'm going to get into that in just a moment. Okay, so we can add this detail to our list. An acid turns blue litmus paper red, and a base will turn red litmus paper blue. The last thing that I'm going to say about this is that an acid and a base, I'm going to circle these. An acid will react with a base to form water and salt. A base will react with an acid to form water and salt. Now, what I want to show you guys though is what does an acid do or how does an acid react with water? But before I show you that, let's go ahead and say we've talked about, just kind of as an internal inventory, we've talked about our theories of acids and bases. So we've talked about the Arrhenius theory, Bronsted-Lowry theory, and now we've talked about properties of acids and bases. Based on those two big things, how are you feeling about your understanding of acids and bases compared to how you started this class? Do you feel one, I feel like I've improved? Two, I haven't improved at all. Or three, where are we? How do you feel about what we've covered so far? And I'm optimistic for lots of ones. And I'm getting lots of ones. So this is great. Now, what I'd like to see and like to show you guys is how does an acid respond in water? What does an acid do in water? Okay. Now, what we have here is an example of an acid, and this is hydrochloric acid, HCl. I know that whenever I typed or wrote HCl, you were probably like, wow, that formula, where'd that come from? Not really. I know you guys weren't like that because we've done Lewis structures, so you guys are familiar with that. So if we had HCl and we reacted it with water, what is going to happen? Well, this is an acid. So just to kind of anticipate, we've got this H that's highlighted. Something special is going to happen there. That H is going to be moved. Huh. So here's our two products. We've got to bring back some older terminology, we've got a chloride ion, and then we've got a hydronium ion. So we talked about the hydronium ion, or I mentioned the hydronium ion earlier. So that's an important thing to think about and anticipate. We've referred to HCl as hydrochloric acid, and then this guy right here, water. It's an old favorite. I like it. What I'd like you guys to do is answer this poll question. And think about this in just like how you read, left to right. Which of these molecules, HCl or H2O, and I couldn't do the subscript because Zoom didn't want me to. Not really, it just couldn't. Is it HCl, that's the proton donor, looking from left to right, so here to here, or is it H2O, that's the proton donor? I'm going to give you another maybe 10 seconds or so. And I gotta say, you guys are really knocking this one out of the park. We are at, yeah, I'm gonna go ahead and stop it right now. I'm gonna share the results. 74% of the class selected HCl, and you're right. The donor is the one that gives up, or not gives up like it's defeated, but instead it gives away that proton. So this proton right here, well, if you look at this substance on the other side, we've got Cl minus, that chloride ion. So HCl gives up the proton. I'm going to stop the share because I got another poll question coming up in just a second. Now let's look at another example, another reaction with water. NH3. We talked about this one. This is ammonia. Ammonia. Could anyone add to the chat what is this is the active ingredient in which cleaning solution? Just how? There we go. Windex, perfect. Ammonia is the active ingredient in Windex. Okay, so let's see how ammonia, and if you remember, ammonia was one of the sticklers, and it was one of the issues that Arrhenius encountered as like the scientific community saying, "Hey, man, what do you got to say? Like ammonia is pretty big deal. How are you classifying that as an acid or a base?" Well, ammonia plus water, what does that look like? Okay. So again, we've got that H that's maybe a little bit of foreshadowing there, but let's just take this all into consideration. We're starting on the left-hand side, so I'm going to put an X and we're moving to the right-hand side. What are our products? So how does ammonia, NH3, react with water? And what are the products? Okay, we've got this guy right here. Oh, NH4 plus, and then OH minus. Oh man, that's interesting. That's new. That's a little different. Now I want you guys to answer this. Looking at this, which one of these is the proton donor? Is it NH3 or is it H2O? I'm going to give you about 40 seconds or so to answer this because I've got a follow-up question that relates to both of these reactions. And you know what? We're definitely trending in the positive direction. So we're going in the right way. I think an important thing to think about when you look at this sort of question is remember you're reading from left to right. I I remember always struggling with okay, I'd look at a reaction and be like, okay, well it's here, but then as a product, what, huh? And I just sort of reset myself. Now I'm going to go ahead and stop the poll right there. I'll share the results. We got about 67% with the correct answer that H2O is the proton donor. I'm going to stop the share on that. And our proton donor is H2O. I mean, it was kind of a tell with the highlighted H, but what I want you to think about is how has this changed? How has this changed when you look at the products? NH3 becomes N, one, two, three, four. Oh, and then there's this positive. That's, if you remember the list of polyatomic ions that you get the polyatomic ions on your exams, but that's NH4 plus. That's ammonium. Subtle difference, but nevertheless, ammonium, not ammonia. Then, so this becomes this. H2O, well, it gave up that hydrogen. So that's gone. So now this is just a hydroxide ion. Okay. Now, the follow-up question that I have to both of those is this right here. Based on these two reactions, looking at both of them, is water acting as an acid or a base? And I want you to feel comfortable with that language of acting or behaving as, um, because in certain circumstances, something might behave in one way different from it would otherwise. For example, if I go to eat at a fine dining establishment, chances are I'm going to wear a different shirt than if I were going to a tailgate. Just my personal lessons learned. Okay, so now what I've got is water acting as an acid exclusively, a base exclusively, or is it an acid in one and a base in the other? And we're trending in the positive direction, but let's just kind of go ahead and look at each one of these. So H2O in our first reaction. Does this H2O, does it gain a hydrogen or does it lose one? Oh, this H2O becomes this right here. Oh, and that H is new. It gained that hydrogen. Okay, now what about H2O right here? Okay, that H2O becomes this right here. So here it loses. So this accepts a proton and this donates. Give me a T in the chat if you think that accepting and donating are opposites. I'm going to go ahead and end the poll. Yeah, they're opposites of one another. And what we have to illustrate that is that, well, water acts as an acid in one reaction and a base in the other reaction. So in our top reaction, water accepts a proton. Therefore, in our top reaction, water is acting or behaving as a base. And then in our bottom reaction, water is donating that. So it is acting as an acid. All right. Now, one of the things that's been kind of hovering over us that I haven't really explicitly talked about is pH. Give me a zero in the chat if you've ever heard of pH prior to this class. Okay. Maybe it's in a previous chemistry class, maybe it's in a previous science class. Um, but a fair question, or maybe you worked at a pool. What is pH? pH is a concentration measurement for hydrogen ions in a solution. So when we talked about concentration, we talked about molarity. And anytime you see something bracketed like this, H plus, that is a way of communicating molar concentration. I want you to feel comfortable with H plus, but I also want you to feel comfortable with hydronium ions. And the reason for that is this right here. Hydrogen ions, when they are in solution, are going to almost immediately react with water. And when they react with water, they're going to make a hydronium ion. More times than not, we're going to talk about hydrogen ions, but if you see H3O plus, I want you to think about the molar concentration of hydronium ions is equal to the molar concentration of hydrogen ions. Now, this is kind of a good starting point. If a solution is not neutral in pH, then it's going to be a little bit different. But for the time being, this is what I want you to be operating on. Hydrogen ions, H plus, are basically equivalent to hydronium ions. Now, although hydrogen ions or the hydrogen ion concentration tells you about acidity, really the hydronium ions tell you about how acidic a solution is. So this substance right here, H3O plus, is going to tell you about how acidic a solution is and the molar concentration of them. That is effectively going to be the same as our H plus. Okay, now with that, if a substance makes lots of hydrogen ions, then it makes lots of hydronium ions. Could you give me a W in the chat if you follow that connection between hydronium ions and H plus? Okay. Now, when we think about a solution, when we think about concentration, if you have a solution with a hydrogen ion concentration of 0.01 molar, what that means is 0.01 moles of hydrogen ions in 1 liter of solution. So, oh wait, what's just that? Okay, sorry about that. I'm sorry, I jumped ahead. Um, so let's go back a second, I apologize. When I say lots of hydronium ions, I want you to think about this. This lots of hydronium ions. Am I talking like 10 per liter or anything like that, or 100? Not really. When we deal with acids and bases, we're looking at concentrations like 0.000001 molar or 0.01 molar. Both of these are fairly high. So what this means is if you had a hydrogen ion concentration, and just for you guys to kind of keep along with me, I'm going to use this H plus more than I use H3O plus. Could everyone give me a X in the chat if you follow that? Okay. So if I had a hydrogen ion concentration of 0.01 molar, that is the same as 0.01 moles of hydrogen ions in 1 liter of solution. Okay. Now, if we were to look at that and say, all right, well, that's one solution, let's compare another solution. H plus this 0.001 molar is going to be 0.001 moles H plus per 1 liter. Okay. Now, what I want you guys to look at with me and answer this in the chat, we've got solution A. I'm going to circle all of this. Here's solution A with a hydrogen ion concentration of 0.01 molar, and solution B right here with a hydrogen ion concentration of 0.001 molar. Could you tell me, A or B, which one of these solutions has the higher hydrogen ion concentration? More moles of hydrogen ions per liter of solution. Okay, so that's an important thing to think about and to be aware of. So I'm going to erase all this over here. That's where I'm going to excuse my language, but the brain fart. If you have a solution with a hydrogen ion concentration of 0.01 molar, as we have with solution A, and we have another one with solution B with 0.001 molar, the pH of these two solutions differs by 1 unit. Now, between these two, if we go back and we think, all right, an acid donates a proton and a base accepts a proton. And everyone said that solution A had a higher H ion concentration. Which solution do you think is more acidic? The one that has a high hydrogen ion concentration or the one that has a low hydrogen ion concentration? A or B? Go ahead and add A if you think that's more acidic, or B if you think that's more acidic. Okay. Yeah. Between these two, A is the more acidic solution because it has more free hydrogen ions. So more acidic. Now, this point down here, the difference of these two solutions, the pH of these two solutions changes by 1 unit. Okay. So when we talk about the pH of a solution, we give numbers as opposed to giving, oh, well, the hydrogen ion concentration is 0.0000001 molar or zero point zero 0.01 molar. Instead, we give numbers that are not exclusively round numbers, but they have a nicer range. And that range is 0 to 14. Okay. Now, how do we do that? How does this work? Well, could you give me a 1 in the chat if you have ever heard of the log scale? Or a log function? Okay. Now, when you look at a log function and we relate hydrogen ion concentration right here to pH, there's a little bit of math involved. But what I want to do is I want to show you this graphically. And we're going to work through some examples and we're going to build a table together. So this right here is a log graph. Specifically, this is a log base 10 graph. Now, if we look at which axis is this? Is this our Y or our X axis? Yeah, it's the Y axis. And then right here, erase that. That's our X axis. Okay, great. So when you look at this blue curve, and if you're looking at this and thinking, oh my gosh, this takes me back to algebra 2, deep breaths, deep breaths. We're getting through this together. Okay. When you look at this graph, what I want you guys to see is y equals log base or log 10 of x. Okay. Can everyone give me a 8 in the chat if you follow that? Not necessarily, oh, I can see that graph, but okay, this is the equation that you want me to get. I got it. Okay. Now, what I want you guys to do with me is I want you to take the number 10 on my x-axis, and we're going to play a little game of Battleship. And what I want you to do is figure out what is the value for y when x is equal to 10. So what is our coordinate there? So when I type in, or whenever I say y equals log 10, and then I put 10 as my x value, I got an immediate response. I got a private message response. I'm not going to share it with anyone. What is y? And so basically, I just need to look at my graph, looking at my blue line. Could anyone add to the chat and tell me what is the value for y? So what is my y-axis? Becca, spot on, 1.0. Perfect, great. Okay, so I think that I'm going to make a little chart here. X value and the y value. So if my x value is 10, my y value is 1. Could you give me a B as in boat, if that makes sense to you, or if you can see that? Okay. Next up, what I'd like to do is I'd like you to say, all right, well, let's up the ante a little bit. What about when my x value is, I can go with, I'll pick a number 30. My x value is 30. Give me a rough estimate of the y value. Okay, 1.5. I agree with that. Now, it's tempting, and I'll need you guys to share a U in the chat if you agree with this statement in just a moment. It's tempting to say, oh, okay, well, my change whenever it was 0.5. When I went from 1 to 1.5, my X value went up 20. So then whenever I go up again to 2.0, well, then my X value should be 60. Could you give me a U in the chat if you agree with that logic? Just looking at the values, not looking at the graph, but looking at the values that I've written in the table. And if you're looking at and hearing me and you're like, that doesn't make sense, I'm looking at the graph, good. That means you're like, I'm not going to be distracted by this. Okay, so what I want somebody to do though is let's now switch it a little bit and say 2 is equal to log 10 of what number? What is my x value when my y value is 2? Looking at my blue line there. I got a private message with the right answer. Maddie, it's 100. Victor, yeah, you're pretty darn close. If I could have extended this graph a little further, or if I had not just lifted it from Wikipedia, which that's where it came from, yeah, you'd see that if this continued on, well, then that would be 100. Okay, so my x value is 100. Now, what I want you guys to do is I'm going to erase this 30, and I'm going to erase this 1.5, that kind of intermediate number. And I'm going to move up 100 and 2.0. Okay, so could you give me a 3 in the chat if, hey, I've seen this before, or I've seen something like this before? Okay. It's maybe been a minute, but this log scale is what we use for pH calculations. It's power of 10 scale. Now, if we were to go on from here, and let's say you can't really look at this graph and say this, but if you said 10 to the okay, so this is the pH, this is the way that we use and do pH calculations. Now, we make a minor modification to this because when we're talking about hydrogen ion concentrations, we're talking about super small numbers, fractions of one. So what we need to do is use this equation right here. pH is equal to log base 10 of your hydrogen ion concentration. But this is right here for a reason. Now, what that means is if you were to use your calculator and take pH is equal to negative log of, let's say, 0.1. And I'm going to go ahead and share my calculator. I'm going to plug that in. Say 0.1. I'm going to share my calculator. There we go. And does everyone see the log function? -1. Oh, wait a minute. Does anyone remember what I said the pH range was? Do you have a negative pH from the scale that I mentioned a little bit ago? The range for a pH is going to be 0 to 14. Okay, so is -1 outside of that range? Absolutely. Now, coming back here, that's why we have this negative right here. Because if you were to type in log of 0.1, you're going to get -1. But if you type in negative log, then you'll get +1. So what I mean by that is, or what I want you to think about that is when you look at this value, this hydrogen ion concentration, one way to think about it is how many times did I have to move my decimal in order to get a whole number? So what I want us to do is to put some of these numbers that correspond to hydrogen ion concentrations on the next slide. Okay. Now, could everyone give me a 1 if you're good, a 3 if you're decent, and a 5 if you're very confused? Okay. All right, so I've gotten some 3s and 5s. I was trying to illustrate the log scale and show the change of X values and how that is impacted or how that impacts the Y values. This next table, I'm hoping, will address some of these, or address some of the confusion, because this is kind of how this log scale applies to pH. So these numbers right here are all reasonable hydrogen ion concentrations to have in a solution. Now, with that, okay, we've already talked about and we kind of looked at, well, how do these vary in terms of more concentrated or less concentrated? Could everyone give me a Y in the chat if they follow how all of these show different hydrogen ion concentrations? Okay, great. Now, with that in mind, let's plug in log of 0.1. negative log of that. Now, what I'm going to do is I'm using the calculator that's built into Windows. And so what I'll do is I'll type in 0.1 log. That's going to give me -1. I'm going to be transcribing this onto the table. That -1, since I have the negative in the equation, is just going to be, I'm just going to write it down as 1, as a positive value. Okay. Now, if I type in 0.01, does anyone want to guess what that value is based on or actually, I'll hold off on guessing there. Okay, so that's -2. Again, switching it to a positive value, my pH is 2. Okay, now if we were to say 0.001, could anyone guess what the pH for a solution with a hydrogen ion concentration of 0.001 is going to be? And you can kind of look at this and say, oh, Kelly's got it. How many places did I move my decimal to make it a whole 1? Well, log -3, that's going to make it +1. Or so, sorry, that's a +3. Then from there, I'll do the same thing with 0.001, oh, 0.3 of them, log, that's +4, 0.00001, log, that's going to be +5. Okay, so I'll complete this table right here, right there. So my pH is going to be 4. If my hydrogen ion concentration is 0.0001. pH, if this is my hydrogen ion concentration, my pH is 5. Now, I've got some, before I ask a poll question, or these poll questions, what if my hydrogen ion concentration is not a nice round number? What if my hydrogen ion concentration is 0.0039 molar? Would you expect the pH to be greater or less than 2? Put G for greater than or L for less than. Yeah, getting lots of G's for greater than. I would expect my pH to be greater than 2. Because if you compare this number right here to this number right here, this number is lower than that. So if the hydrogen ion concentration is lower, that means my pH is higher. So I'm going to give you guys these poll questions. There's 2 questions. The first one is, if a high hydrogen ion concentration indicates an acidic solution, which of the following hydrogen ion concentrations is most acidic? We got 0.0001, 0.001, 0.1, cannot be determined from the provided information. Then the next question, based on the table that we produced, as well as our knowledge of hydrogen ion concentrations and acidic versus basic solutions, which pH is most acidic from the options below? Take a minute because there are 2 questions, so it's a little bit involved, but I want you to see that how these 2 questions are kind of interconnected with one another. And you know what? You guys are doing a great job because I'm seeing the numbers sort of trending correctly for both questions. So that's great. I'll give you another few seconds to answer this, maybe 15 seconds to think about this one. Okay, I'm going to go ahead and stop the poll right now. and I'm going to share the results. Okay, so one of the cool results that I see is the first question is, if a high hydrogen ion concentration indicates an acidic solution, which of the following hydrogen ion concentrations is most acidic? zero point 0.1 molar is the correct answer. That was selected by 63% of the class. Now, high hydrogen ion concentration translates, based on this table, to a low pH. So high hydrogen ion concentration to a low pH. Those two are correlated with one another, or connected with one another. Now, based on the table, as well as our knowledge of hydrogen ion concentrations and acidic versus basic solutions, and kind of thinking back to what we saw over here, we said that the 0.01 molar solution was more acidic than the 0.001 molar solution. So when we had the higher hydrogen ion concentration, we had the more acidic, therefore, we had the lower pH. So which of the pHs is most acidic from the options below? And 61% of the class selected 1. You're absolutely correct. Now it's really tempting to or it's easy to get kind of tripped up on this and think, oh, well, higher number means more acidic. But remember, the scale ranges from 0 to 14. Now, to illustrate that with some examples, we've got this right here. This scale is a good one to think about and try to kind of land some different substances on that. And what I mean by that is to remember the range, 0 to 14. Then think about, okay, if we're in the middle, our pH is 7 because between 0 and 14 is 7. Now, anything that is from 0 to less than 7, that is an acidic solution. And then from 7 to 14, that is a basic solution. So basically, I hate to say the word basically whenever I'm talking about acids and bases, but habit. Low pH, I'll write this down. Low pH is high hydrogen ion concentration. Then high pH is low hydrogen ion concentration. And is that. And these are acidic and basic. If you can remember this, that's going to be very helpful and powerful for understanding acidic and basic solutions. And that's our kind of quantitative or our measure of, well, is a solution acidic or basic? Now, I'll leave this up, but now I'm going to give you these different poll questions. So a solution with a pH of 10 is acidic, basic, neutral, or toxic. And then a solution with a hydrogen ion concentration of 0.001 molar has a pH of what? So I'll leave this up as just sort of a reference that you're free to use for this. And you know what? The overwhelming majority for the first question, you're pretty much spot on. We're at 65%. Oh, yeah, we're doing great basically in both of these questions. I'm going to give another 10 seconds. We're at 48 seconds, so I'll stop it at 58 seconds. So you got about 10 seconds left to answer this question. And scene. Okay, so I'm going to share the results. pH of 10 is basic. Great job. And a solution with a hydrogen ion concentration of 0.001 molar has a pH of 3. The first responses that I saw were 2, and I think what people were doing was they were like, oh, it has something to do with zeros. Remember, you've got to get it to 1.0. So how many times do you have to move the decimal? I always think about it as, okay, if my hydrogen ion concentration is 0.001. Then I'm moving it 1, 2, 3. So I had to move it 3 places. So pH equals 3. I know whenever I first started doing this sort of thing, using that little trick, I would be like, oh, well, I moved it 3 places. One. I would make that mistake. Don't make that mistake, everyone. Okay, stop the share there. Now, here's those poll questions again. Here's those poll questions again. We got a little bit of time. So I have these 2 demonstrations, and then I've got some last poll questions. I wanted to share with you guys these 2 demos, and these are on the PhET web page that we've used before for demos. And this just I like these because they give you a visual of kind of what's happening in a solution. So here what we have is we can adjust the solution. We can go to a battery, or actually, we'll first go with water. What's the pH of water? 7. Ideally, the pH of water, pure water, distilled or deionized water that you get at the grocery store that you put in your iron, that's going to have a pH of 7. Now, if instead we got battery acid, it's going to have a very acidic pH, a pH of 1. We swap that out to milk. Well, milk is a little bit more basic than battery acid, but it's still kind of acidic. Now, the last thing, coffee, it's pH of 5. Okay, now this is just giving an illustration of some different solutions. What I want to show you about this, though, is what happens when we add water, when we dilute the solution. Okay, so if we're diluting the solution, that means is our hydrogen ion concentration, going to go up or is it going to go down? Give me a U in the chat if it's going to go up, a D if it's going to go down. We're adding water. That's just pure H2O. Okay. So when we add H2O, and I think that I can, yeah. This is H2O. The thing that's giving the protons is the acid. So if anything, our hydrogen ion concentration, let's see what happens. Wait a minute. Our pH went up. So what does that mean for our hydrogen ion concentration? If our pH goes up, what does that mean does our hydrogen ion concentration go up or does our hydrogen ion concentration D go down? If the pH goes up, that means our hydrogen ion concentration goes down. Okay, so one way to think about this is, I'm going to move this over here. That's yeah. Okay, then sorry, my annotate tool, I got to pull that back up. Okay, good. Okay. So this H2O that I'm adding, there aren't any hydrogen ions there. The coffee brings all the hydrogen ions. So H2O or the H plus, that was basically fixed. That is not going to change. But the solution volume goes up. So when the volume goes up and the hydrogen ion concentration stays the same, that means that our hydrogen ion concentration effectively goes down as we add more water. Think about this as more water is diluting. Okay, does that make sense? Give me a Y if you follow that, a Z if, wait, that doesn't make sense. Okay. Okay, so now I'm going to reset this and I'm going to get another example. So let's kind of anticipate the same sort of thing. Clear all drawings. Let's go ahead and get a solution of chicken soup. Wonderful. pH of chicken soup, fairly acidic. If I add more water, ooh, great question. What if I add it? Let's see. Drain cleaner. That's going to be pretty basic. Okay, so I got the question from Kelly. What if you added water to a basic substance? Okay, what we're looking at then is we're going to see our pH actually go down. If we slowly but surely add enough water, or if we were to add enough water, we're going to continue to dilute what is in this solution. So we'd get back to a pH of 7 eventually. It would take a very long time, but we would eventually get back to 7. Now, this, we've primarily focused on acidic solutions. We're going to talk about basic solutions a little bit more on Thursday. But this is a great primer because when it comes to acidic solutions, what are we what do we have? We have a bunch of hydrogen ions. When we have a basic solution, well, something can gain a hydrogen ion, and that something is a hydroxide ion. So we'll get more into this on Thursday, but now I want to show you, actually, yeah. So we'll get more into this on Thursday. Now, I think what I'm going to do is I'm going to go ahead and give you the last poll questions. I got 3 of them. So Kelly, I'm sorry, does that answer your question for the time being? Okay, okay. So we'll get back to that on Thursday. In the meantime, though, the last few slides in this slide deck, yeah, I'm going to go ahead and stop my share there. Then I'm going to show you the last question. I've got 3 questions here. And whenever you're done with these, I'll just say thank you guys very much for coming to class, participating. I hope that your understandings of acids and bases grew, and I hope that you're feeling a little bit better about acids and bases. And we will continue talking about them on Thursday. The first question is, what is an acid? So think about the different theories that we've discussed. Then the next question is, what is a base? And then the very last one is, how do the Arrhenius and Bronsted-Lowry definitions differ? So basically, why do we have multiple theories? And again, Arrhenius likes to go swimming. Bronsted-Lowry, they like to transfer stuff. So after you answer these, I'm going to hang around, obviously, to look at the results. And then if you want to join me in office hours starting in about 13 minutes, I will see you there. But I'll leave this open. We got another 3 minutes till class is done. And if you have any specific questions for me, please feel free to shoot me a message. And I can, yeah. But other than that, thank you guys very much for coming to class. See ya. Oh, and I'm going to stop my recording.